So then, now that we've laid the groundwork for chapter 23, let's get into a little bit more detail and review what this chapter is all about anyway. So, like I said before, it's pretty much a continuation of chapter 22, and really what we've learned so far is how to look at the particular substituents on the aromatic ring and predict how they're going to direct where the electrophilic aromatic substitution takes place. So we've covered sections 1 through 4, and in this mini lecture we'll cover reactivity, how these substituents impact just how reactive the aromatic ring is, because as we know, it's not real reactive. After that, we kind of try to have a little interlude where we pull it all together and look at how these substituent effects and reaction conditions impact the outcome of electrophilic aromatic substitution reactions. And then you think, well, let's just leave well enough alone. Let's be done with it. But no. There's 3 other topics that round out the chapter that just, as usual, kind of throws a little curveball at you. All right, so what do we got? Reactivity in electrophilic aromatic substitution. We know one thing for sure: the aromatic ring is our nucleophile because it's electron rich. Granted, it's not a very good nucleophile, but it is our nucleophile. So since it's our nucleophile, anything that we put on the ring that makes it more electron rich will increase its reactivity. Sounds good? Not so much. It's not always a good thing. So benzene is kind of our standard, and here is a diagram taken right out of your textbook, generated by using computational chemistry, e.g. Gaussian. This is an electrostatic potential map that basically is just showing you where the electron density is in this molecule. And the red is the pile O electron density, smack dab in the middle of the ring where that pi molecular orbital sits above and below the 6 carbons. So the point of these diagrams, these maps I should say, are basically to compare the electron distribution when you have different substituents on them. So here is benzene compared to aniline, and what you can see, I hope, by comparing the electrostatic potential map of benzene on the left to that of aniline on the right is that, use your imagination if you need to, but that's a little bit more red. There's a little bit more electron density built up in the ring for aniline. And we can certainly argue that that makes sense on the basis of this kind of resonance delocalization, that the lone pair on nitrogen is pumping electron density into the ring, and if we keep going around and around showing the other resonance contributors, we will see that, yes indeed, there is electron density big time built up in this aromatic ring just because that lone pair is delocalized throughout. So let's finish this out before I move on. Here are a couple of those resonance contributors. And basically, remember, it's not the individual resonance contributors that are important, it's the hybrid. So if I took the composite picture of all that, it would really pretty much look like this guy. More electron density in the center of the aromatic ring. Well, that's not a dramatic difference, but this one really is. So look at what happens when we put a severely electron withdrawing group, woohoo, on the aromatic ring, the nitro group. Look at what happens to that electron density. It pretty much disappears out of the aromatic ring. So what this is telling you is that this guy is really, relatively speaking, unreactive. That electron withdrawing groups decrease the reactivity of an aromatic ring. Electron donating groups increase the reactivity of an aromatic ring. So we can illustrate that in a couple of examples. So benzene, remember, aromatic ring is our nucleophile. It's always our nucleophile. But now when we can compare the relative rates of these two aromatic starting materials, both of which are going to undergo Friedel-Crafts putting an ethyl group on the aromatic ring. We can ask the question, well, which one's going to react more quickly? Which one of these two aromatics, the thioether or just plain old benzene, is more reactive? And of course, what we're going to do is pay attention to the lone pairs on the sulfur and recognize that that makes that an electron donating group, so we should predict that that would be the more reactive aromatic substrate. And it indeed is. So this will react faster. And as we already saw in the earlier mini lecture, because this is an electron donating group, it's going to be an ortho para director. So I get this mixture of the ortho para isomers, and of course in benzene, since there's no substituent, I don't have to worry about directing effects. But the point here is electron donating group increases the reactivity. The top reaction proceeds more quickly. All right, example number 2. Now we're going to compare benzoic acid to toluene. Okay, so you need to familiarize yourself with these aromatic names. So toluene, we recall, I hope, that the CH3 group is electron donating. So this should be slightly activated. And certainly this carboxyl group is electron withdrawing, because we can draw this resonance contributor that shows how there's a positive charge on our carbon directly attached to the aromatic ring. You know, it's not a very good resonance contributor, so if nothing else, what we should do is just look at the fact that in a carboxylic acid or ester or any of these carboxyl type substituents, what's really important is that we've got a strong dipole in that CO double bond. So that's a deactivator, and when we compare the rates of reactions here, we should see not only does this guy go more slowly, but it's a meta director. This will be faster, and again, an ortho para director. So that's it in a nutshell. Activating groups which pump electron density into the ring are generally ortho para directors, and deactivating groups in general are meta directors. Until you look at the halogens. So there's, like I said, there's always got to be a darn curveball. So when we have something like chlorobenzene, it's a little confusing. You know, what can I say? The halogens are just confused. So we know that the halogens can be, they're somewhat electronegative. So we have an inductive effect whereby the chlorine, being more electronegative than carbon, is pulling electron density away from the aromatic ring, deactivating it. But at the same time, when the actual reaction takes place and a carbocation is formed, the ortho para substitution pattern is stabilized because of that resonance contributor. It's not a great resonance stabilization, but you can't ignore the data. When I get chlorobenzene and I do EAS with it with some electrophile, I will, period the end, get the ortho and the para substituted products. That's the data. So that's what we have to pay attention to, and then we go back and explain it. And so our explanation is it's got to be resonance stabilization of the intermediate carbocation, and the fact that it's a deactivating substituent means that must be the inductive effect of the electron withdrawing chlorine playing a role. It's never easy. So, got to look at both electronic and steric nature of the substituents when we're trying to predict the regiochemical and the reactivity outcomes of the electrophilic aromatic substitution reactions. And I've assigned some pretty darn good problems in CARDI to help you think about these two a little